So the second challenge that I mentioned kind of is building a dynamics model. And what we'll find later is that the answer isn't to build a single dynamics model that works for the entire helicopter everywhere. It's actually a non-parametric model that's different for each trajectory. And we'll go into more detail about that too. Okay, another challenge is that it's not even clear what the target trajectory is. Okay, so with hover, like I said, you just say you don't want it to move. So for example, you might want it to do flips. And so you might think, oh, it's easy, I just want it to do flips, so it means just rotate in place. But you can't just rotate in place. You also need to supply a vertical thrust that allows the helicopter to stay in the air. And so now there's this trade-off between flipping in place and providing enough thrust so you don't crash. And what's the right trade-off? How do you make that trade-off? Right? So we need to actually specify the full trajectory, all the positions and orientations throughout the entire flight, such that it's actually feasible. And like I said, I already mentioned the dynamics model. Okay. So the outline is, we'll talk about how to learn the target trajectory, and then I'll go into how to learn the dynamics model, and I'll show you some results for both of those. Okay. So as I mentioned, it's very difficult to specify these trajectories by hand. The required format is a position and orientation over time, and these positions and orientations have to satisfy the helicopter's dynamics. If they don't, then you can't fly it. That's the definition. So what our solution is, we're going to collect demonstrations of the desired maneuvers. So we'll have the pilot fly 5 stall turns of roughly the same height and same parameters and everything. So we just tell the pilot to fly the same thing 5 times. And the challenge now becomes to extract a clean target trajectory from these many suboptimal and noisy demonstrations. Right? So the pilot's not perfect. I mean, they can get these things to fly well, and they're great, but they're not going to fly the same thing 5 times. You can't do that. And so none of those 5 examples he's going to give us are exactly what we want to fly. So what we have to do is kind of average them together and take out the good parts and leave out the bad parts. So let's get an idea of what it exactly is that we're asking for here. So here's a video that shows 6 demonstrations by our pilot, and these are just graphical replays of the data that we logged. And you'll notice that the pilot is actually flying essentially the same maneuvers, but there's a lot of variability between them. They're flying at different rates, different sizes, different positions. And so now our challenge is to take all these things and output a single trajectory that is a better version of all of these that we want our helicopter to follow. Okay, so here's the key idea of this approach. So underlying it is essentially a hidden Markov model, where we have hidden states. And the hidden states here are going to be the trajectory that we want the helicopter to follow. Okay, so at the time 1, it'll be the starting state of the helicopter. At time 2, it'll be the next one, and so on, specifying the entire trajectory. And we don't know what they are, right? That's what we're trying to find out. So we're leaving those empty for now. What do we have, though? We have 2 demos of 2 examples of what the pilot flew. We have a dynamics model, which essentially says what the relationship between these hidden states have to follow, right? You have to be able to get to state 2 from state 1, otherwise the helicopter will crash. And so now looking at this, we've got a bit of a problem here. If you'll notice, demo 1 and demo 2 aren't of the same length. And so what do? Are we just going to average them? Are we going to pick one of them? How do we pick the right length for our target trajectory? So to solve this, what we do is we align these trajectories to the hidden trajectory. And you might wonder how we do that if we start with a blank hidden trajectory. So what we do is we just subsample one of them as an initialization. So we took the first demo, we subsampled it, and now what we're going to do is use an algorithm called dynamic time warping, which lets you efficiently align time series, and will align the hidden trajectory that we just initialized to each of the demos. So what this graphic here is showing you is, for each of the demos, what's the state that's most closely corresponding in the hidden trajectory? Okay, so now we've got each of the demos aligned to our hidden state. What do we do now? So now we have 2 observations at each time of the hidden state. And so what we do is we run probabilistic inference, and we're going to re-estimate what the hidden state should be. Okay, so we set it to blank again, and we're going to re-estimate what it should be from these demonstrations. And to do that, we use an extended Kalman filter smoother. If you're curious about the details, you can ask me afterwards. And so you've noticed that we filled in a better trajectory that used the data from both of these demonstrations. And so you might be wondering how this could work. Like, we initialize it kind of arbitrarily. How does that work? And the answer is that it doesn't work if you just do it once. You have to iterate. So now we have a new hidden trajectory. We can realign both of the demos to this new hidden trajectory. Okay, so now we have new alignments. And then we can re-estimate the hidden trajectory the same way we did earlier. Right? So now we've estimated again. And we repeat this process until it converges, which means that things don't change. And typically, we get good performance after maybe running 2 to 5 iterations of this. And this is all done offline, by the way. This isn't being done online, so this is kind of fine because we're generating a trajectory at this point. Okay, so let's see what the results of that look like. So these are the same 6 demos I showed you earlier, except now our algorithm has aligned them, and we've inserted a new demo, which is the white helicopter. And you'll notice that it really is kind of the ideal version. It does capture the pilot's intent of what he was trying to fly. Obviously, the pilot couldn't fly this perfectly because there's a lot of variation, and it's a very hard control problem. But we can extract his intent. And this is completely automated. Once you have demonstrations, you feed it to the algorithm, you get out a target trajectory. Okay, so let's look at some results here. These are demos that the pilot provided, and you'll notice that they look very different, right? There's a lot of variability here. So the black one here, the black dotted line here is what the algorithm learned, and you'll see that it is a much, much cleaner version of a double loop than what the pilot could fly. Okay, so we've now gone through how to create a target trajectory. Now we have to learn how to follow that target trajectory, right? So this is just the first step of the problem. If we use the same methods we did before, the helicopter would still crash, as you saw.